Okay, so what we're going to do is look at another application of what's called Bayes' theorem. So here what we have are three lines of vegetable sealers, canned vegetable sealers. And this column tells me how much each line contributes to the entire production line. So naturally notice that those add up to 1, as they should. Otherwise, there's either missing information or too much information, right? And what we're told here is the proportion of each line that is defective. So the question becomes, once, and again, the assumption is that with the inventory, that, if it gets stored or whatnot, once it's stored all together, we have no idea where they came from, which line it came from. So the idea is, if I know that I have something defective, which line did it most likely come from? And then which line do we have to make a visit to and see if things are operating okay? So here's the thing, though. So let's look at what we have here. So we know that the probability that it came from line 1 is 0.40. That's given from the information there. The probability that it came from line 2 is 0.35. And the probability that it came from line 3 is 0.25. Now, those defective ones are linked directly to the line. So this says that the probability that it's defective, given that it came from line 1, so again, if we know it came from line 1, we know that it has a 5% chance of being defective. Defective given line 2 and defective given line 3. So we have a 10% chance here and a 7% chance there. So, how do we start this? Well, what do we want? We want to know the probability that, again, flipping it around, the probability that it came from L1 given that it's defective, or L2 or L3. So we're looking for which one of these is highest. So, how do we organize this information? We look at a tree diagram. So when we start this thing, there's 3 possible roads we could take it first. We know it could come from the first line, the second line, or the third line. So a 40% chance here, a 35% chance here, a 25% chance here. From there, we know that the case is either defective or it's okay. All right, so line 1 has a 5% chance of being defective. That doesn't look too good. Give that another try. 0.05, great. Which means we have a 95% chance of being okay. We have 10% of line 2 is no good. And we have 7% of line 3 is no good. Now, since we're focused on finding this probability, so let's just say I was going to write this down here. The probability that it came from line 1, given that it's defective, would be the probability that it's line 1 and defective over the probability of being defective. So I just want to know what the overall probability of being defective is. Well, that means I need to look here, here, and here. So if I multiply along the branches, actually we'll find them all anyway. This looks to be 0.02. And that means this should be 0.38. Again, observing, that just tells me how the 40% from A is broken up. So if we keep doing this multiplying, that's 0.035, line 2 and defective. So this one is line 1 and defective, line 1 and okay, line 2 and defective, and the like. So finding line 2 and okay, multiplying along this branch followed by that branch, we should have 0.315, and again, observe, they add up to 0.35. So line 3, 0.25 times 0.07, that should be 0.0175. And 0.25 times 0.93 should be easier to do, but just to make sure of the math using a calculator, 0.25 times 0.93 is 0.2325. And yes, those do add up to 0.25, so we're good. So now remember that these 6 outcomes on the right here make up the entire sample space for this experiment, because we're looking at 2 things. We're looking at where did it come from and is it defective? So for the probability of being defective, we only have to look at these 3 terms right here. And the beautiful thing is, this makes it easier to figure out which line is likely most responsible for a defective item. Now using L1, or list 1 as, or line 1 as a starting point, the probability of being defective is just the sum of those 3. And line 1 and defective is 0.02. Now, we could calculate that out, but the goal is to figure out who is likely most responsible. So to understand what's happening here, let's look at the other 3. Now notice that the numerator of L1 given defective is just what I have shaded in purple here, the 0.02. So L2 and defective would be 0.035 over whatever this sum is. And likewise for L3, 0.175 is the overlap, and it's the same thing. I'm just going to put that right there. Now, since they all have the same denominator, that means the one with the biggest numerator is the winner, or in this case, the loser. Line 2 is likely most responsible. And if we actually compute that out, it is roughly, so we take 0.035 and divide by 0.035 plus 0.02 plus 0.0175. It is just shy of 50%. So that's where we look first. And again, that's not certain, right? That is just who is most likely. So it might not have come from line 2. It could have come from line 1. It could have come from line 3. But that, again, is how we use probability to make some business decisions. So I thank you for watching.